Welcome back, everyone, to our continuing session on data AGN. And our next talk is going to be given by Aurora Muller-Sánchez.
Okay, thank you all for being here. I'm going to present the results of my master thesis. I work in the strong base in Mexico City, and my project is the 3D kinematic analysis of the dual AGN system, known as my current 266. I work also with the previous two speakers, Héctor Javier and Erika. I'm going to speak really briefly about dual AGNs. They represent an advanced merger stage. Durations about 100 megahertz. They have predicted separations using 1 and 2 parsecs. They're dominated by dynamical friction, and there are proposals of AGN binaries before the supermassive black hole cosmos. Our study is centered in this specific galaxy. As we can see, this is a complicated galaxy with a lot of dust, a lot of filaments, and a specific super ring associated to this specific galaxy, the Antarctic galaxy. This galaxy was studied using multi-wave observations by Mazzarella in 2012, and this galaxy was classified as a luminous infrared galaxy. And they detected 2 X-ray sources. We know that X-ray emission is important to detect dual AGN systems. And here we can see the X-ray emission, SHARP-ANext and soft X-ray. And we also we can see radio emission of both of the galaxy, and in particular in this specific galaxy, we can see also radio emission in the center. The separation that Mazzarella showed is 5.6 kiloparsecs, and he shows the black hole masses around 2 and 2.8 and 2.3 and today's masses. There's also another interesting analysis of this galaxy in the optical bands in 2021, and we can see here an image of this long sky survey. And we can see the fit of the emission lines. This is a long-stay study, and we present a fit of the emission lines using a broad line for the long emission lines. Classifying this galaxy as type 1. In our research group, we use data from telescopic anomalies and Megara Spectrograph. We study the galaxy in the optical range with integrated spectroscopy, and the integrated unit is important Megara Spectrograph. We have 3 pointings of this galaxy. Here we can see the 3 pointings overplotted in the slow digital sky survey images. And we can see in the 3 pointings we obtain data in the blue and the red optical range. We have a spectral resolution around 5,000, and our observation date for all of this data is 2023. We also reconstructed with all of these pointings, we built on one side to analyze the galaxy, extend the field of vision of Megara, and also to increase the signal-to-noise rate of this study. We also use MapLine, already 80%, and we can see that MapLine works specifically well with interactive spectroscopy and uses NCMC analysis to find the emission, the fitting of the emission lines. After we did some tests about in our data, we found that we can fit for the morphing movement 2 emission lines. One is this one, and we also found there's another asymmetric profile in our galaxy that is suggesting the presence of a window. And you can see also the same behavior in the H alpha region. For the southwestern nuclei, we also find a second component in the spectrum. The best thing shows the second component too, in the H beta and the H alpha range. Because we wanted to do a kinematic analysis of this galaxy, we also built continuum maps of the H alpha and H beta. We also designed these regions. This is specific regions with 3 arc-second to find the position of the component. Oh, I forgot to mention that this specific number is because we wanted to cover twice the size of the constant function distance. That is a resolution figure. And here we can see the velocity, especially the small velocity maps of the galaxy for the H alpha and the H beta. We also present here 12 flux maps for the nitrogen 2 and oxygen 3 with the regions of the nuclear plotted. And in this specific map, we can see a series of nodes in the southwestern nuclear that we associated this behavior with the process of merger. In this plot, we show the spatially resolved kinematic along a set of defined paths. We designed these paths to going across to isovelocity curves of the galaxy. And in this specific path, number 4, we can see that there's a change of velocity around 70 kilometers per second. Here's the beginning of this path and the end, and going outside the northeast movement, showing, suggesting the presence of an outflow. And this also supports our hypothesis of the fitting of the emissions. We also classify this galaxy with especially resolved BBT diagrams, where we find the northern nucleus be an opposite, and the southwestern nucleus is strong AGN. And we also developed this tree diagrams where the southwestern nucleus falls in the AGN region, and the northeastern nucleus falls encompassing the star forming and light. Because our results are not conclusive, we also use the one diagram from St. Fernando's 2011, and we can see in this visual result 1 that both nuclear fold is from the AGN region. Because we do not have the certainty that this galaxy is not only associated to star forming regions, we also use another diagram, use the dispersion, velocity dispersion of the H alpha. And both nuclear falls in the strong AGN region. And my summary for this study is the northeast nucleus has already detected. That is not associated to the previous studies on Asteroid in 2012. And we have extended emission to the northern nucleus across the field of Niagara. And Mazzarella also showed that it's X-ray radio emission that is characteristic to AGNs. And we have also a nuclear region that contains a large amount of ionized gas. And with our diagnostic diagrams, we know that it's not associated with nuclears. We have diagnostic diagrams, a UPT diagram, composite storm liner for the northeast nucleus, and we also have this secret classification for the southwest nucleus. And with the other diagrams of classification using the cumulative pH alkaline and the description of the cities of pH alkaline, we found that all nuclears from AGN, and this particular galaxy, which is the flux maps, we also find this oxygen-free regions, a series of nodes associated with the merger process. We mentioned the nucleus separation using nuclear, and we found that it's 5.8 kiloparsecs. And our conclusion is that magnetic clouds 266 is the regions. And that's
Question.
Thank you for the very nice talk. I was curious to know what's the interpretation of the radius of the nuclear region? Is this a big issue, a combination, or you have a radius source in between? Yeah.
yes, this particular galaxy has a crazy emission source. Our analysis is centered on range spectroscopy. We only know that this part has a lot of ionized gas, has radio emission. We don't have an optical emission. We also don't find this rate data that's specific.
What's the wavelength of this radio data? It's 20 meter or it's 60 meter?
It's 20.
20.
Yeah. 20. It's yeah.
Other questions?
Yes, this is the this is a interesting part because we are exploring that that is the main trend that produces this emission. And we don't found this is a stuff from here because we can see the emissions, even the emission ones, well, and this is also another that we use the secret. Because exactly in this part we have two observations of black volume of spectral impacts for 6 times exposure time. And we can see the big emission lines of effects. Now we don't see an emission that indicates that it's we see that something that is in here is emitting also in the network link and very administrative.
I was puzzled by the southwestern source, especially the X-ray. The X-ray image that you were shown has some extra emission on both the left and right side. Is that related to your different nodes that you had in the southern source, or have you explored that?
Are you asking me
About the southwestern, the one that has four nodes? The oxygen-free map that you say is probably an outflow or wind or something. Is that? Have you compared that with the X-ray image that you showed first?
No, there haven't used X-ray data to compare exactly with your galaxy specific, but I mean the X-ray data didn't show any.
There is something that I'm asking on the 7 kV map.
So you think there is some X-ray that you can't really
I don't know.
We haven't, yeah.
I suggest you explore.
Any last questions? All right, let's thank our speaker once again. So our next speaker is Paolo Saracco.
Good morning, everyone. I am Paolo Saracco from the Observatory of Aurora and Milano. I thank the organizers who also to this SHARP, a new generation, a concept start of the new generation spectrograph from the extremely large text. Let's see what is SHARP. SHARP is a name-infrared multi-mode spectrograph conceived to exploit the capabilities of the extremely large telescope basically to reach the finest reachable flux, the sharpest angular resolution over the widest adaptive optic corrected field. SHARP makes use of multi-conjugate adaptive optic units such as FAIR, the one from ELT, which correct for atmospheric turbulence a large field, reaching the diffraction limit of the ALT, which is 12 meters. SHARP is composed of two main units, Nexus, an entheogen spectrograph fed by a configurable slit system, and Vesper, which is a multi-integral field. SHARP works over the wavelength range 0.95 to 45, and we decompose at the next isotope sparkling polarity. We will see something more about this at the end of this. Briefly, these are the main properties of SHARP. Nexus, the entheogen spectrograph, will cover simultaneously the wavelength range between 0.95 and 0.55 micron. The field of view is 1.2 times 1.2 arcminutes, over which can be deployed up to 30 slits, considering a slit length of 2.4 seconds. The pixel size is 35 megapixels, and these are the spectral resolution. Vesper covers a slightly narrower wavelength range between 1.2 and 2.4 micron. Vesper is a modular system. It is in the current configuration is composed of two modules, each one comprises 6 probes for a total of 12 probes. Each probe has a field of view of 1.7 times 1.5 seconds each that can be deployed over an area of about 21 seconds times 14 seconds. The sparsity of the pixel is 31 milliseconds, and these are the spectral resolution. Okay, let's see very briefly which are the scientific, what is the scientific rationale behind SHARP and behind these properties. Basically, these are some of the key questions behind SHARP, and all of them ultimately trace back to the main general question on how variables are sent from galaxy structure and how is it cosmic time. To answer this question, we need first of all near infrared, because near infrared allow us to study, to see through the dust, study the dust and shaded regions where often variables are sent, as the stuff from regions, the nuclei of galaxies, of course, and so on. And it is necessary to study, to trace back the properties of galaxies in time, and to probe also the universe up to the very early epochs. This is shown in this plot, where it is shown the observed wavelength of some of the most important atomic emission and absorption lines as a function of redshift. And we see that to grow the area of the universe, we need basically 2.45. The other properties we need is an angular resolution at least of about 30 million seconds in order to sample sizes comparable to those of giant regular gas clouds over the entire time. As shown in this plot, which is shown the linear size obtained by an angle of 30 million seconds, the blue line represents the giant gas clouds. For comparison, the red line is the pixel size, the linear size obtained by the pixel size of the spectrograph. Why giant regular gas clouds? Because they contain up to 10 to the 6 solar masses of gas clouds. They are the main spectral units, the main matter units. They trace the galaxy rotation, the galaxy dynamics, and they are the clouds of orbital clusters and possibly also of primordial population free systems. So let's see two main properties of SHARP. This is one module of Vector, which comprises 6 probes that we call field selector. And this field selector can be moved along the y-axis, and their movement along the y-axis is compensated by 2 mirrors which keep constant the optical path between the collimator and the grainer, so that they all share the same focal plane. And onto the focal plane, onto the focal plane, they form an image like this one as if they were all aligned. Onto the focal plane, there is this laser which slices this image at 31 million seconds. Let's see the configurable slit system of Nexus and the other spectrograph. The slit is formed by 2 parts moving toward each other, and in this up to the position of the target, and this allows us an adjustable slit width and also a perfect centering of source. For comparison, we have shown the micro-characterization system mounted at the respect the JW. But this is not the true peculiarities of this. Let's see. Let's suppose that we are interested in deriving the dark matter fraction of galaxies. We have selected our sample and we have put them into the slits. In order to derive the dark matter fraction, we have to obtain a rotation for all these galaxies. And of course, for aligning galaxies along the slits, we have to rotate the whole field, and we can align at most just one galaxy at a time. Actually, Nexus will align all the galaxies at one time, thanks to the inversion prism, which will fed each of the slits. The inversion prism works in this way: the light enters from above, the green light, for instance, on light, and after some reflection, the green light is exiting from above is on the left. This implies that the field has been input. In this way, by rotating by an arbitrary angle the inversion prism, we can align all the galaxies, since we can rotate by an arbitrary angle the subtended field of each of these. Okay, this is the first optomechanical design of SHARP. Here I shown the cryogenic tank with the system on top, just below the entrance glass where for the light there is the selector system and with the configurable slit system and the field selector of Vesper. And according this system can be moved horizontally, and according to the fact that just below the entrance glass there is the configurable slit system or the field selector, the light will go through Nexus or otherwise will be deviated to the 2 modules on Vesper. Okay, let's see what SHARP can do into the central Kinematic region for dual AGN. This is the same plot was in the beginning, the linear size obtained by the pixel size of SHARP. As a function of redshift, but in logarithmic scale, just to better understand which is the spatial resolution at lower redshift. We see that the giant region is the one, is the central kiloparsec region that can be sampled both from a few parsec at low redshift, up to 250 parsec in the very in the less favorable cases of redshift about between 1 and 3. Let's see what happens in this less favorable redshift range when looking at dual AGN. These are two dual AGNs that we have already seen this morning by Saracco. And on the left, we see there is a dual AGN at redshift 3, the other one at redshift 1 and 2, with separation of about 3.7 kiloparsec and 2.8 kiloparsec respectively. On the left is shown what nexus, hypothetical observation nexus with the measure axis aligned along the slit, and nexus would provide independent integrated spectra along the measure axis at a sampling rate of about 270 parts. This is the pixel size of nexus. On the right, we show what instead could be done by Vesper, which can resolve, spatially resolve this system at 260 parts. This is a slightly different system, sub-kiloparts of the AGN at redshift 1. This is an image obtained at the Large Molecular Telescope from a couple of observation event. And this is the zoom of the nuclear region. And superimposed is the grid of Vesper in red at the resolution of 50 parts. And again, in the yellow is the hypothetical slit of nexus. For comparison, in gray is shown the resolution, the pixel size of this AGN. Okay, let's see what are the prospects of the project, the SHARP project. We will propose SHARP at the next expanding, expanding item. Whose deadline for electoral meeting is 2026 and December 2026. And for that time, the SHARP project has to grow by collecting, by assembling an international consortium, of course. For this reason, we are open to collaboration with potentially interested foreign institutes and, of course, also with individual researchers. I invite you to have a look to the SHARP website or contacting directly if you are interested in SHARP. We are collecting SHARP science book that will be published by Muller-Sánchez Journal. SHARP science book is will be a collection of scientific cases showcasing the instruments' capabilities in different areas of statistics. So I invite you to submit the scientific cases if you think that SHARP can make the difference for your science. Again, all the information can be found on the web page. So, SHARP actually exceeds the observational limits fixed currently by JWST and would allow us to explore the new part that JWST is doing. So, we are convinced that SHARP could take up the bottom left by JWST when it's mission. Thank you.
Okay, thanks, Paolo.
how much is going to cost this enterprise? And it's comparable to the other ideas that are circulating within the community, because I heard about the new telescope, we are talking about only the new.
Thank you for the question. Actually, the expanding horizon is a goal from ISO that took all the money up to 6 million and 50 half of the budget of the EFD to cover all the expenses for this roof. This instruments we believe that they can start to 70, 80 service. So it is completely covered by the budget of ISO.
Yes. Yeah, I don't know the exact specification of all instruments planned for the ET, but could you state what is the unique characterization of this instrument? Mosaic, which is also quite good. IFU, multi-view system, that's fun. So, what is the unique characteristic that SHARP will compare to these other instruments?
Sure. So, unique characteristic is the first one is the angular resolution, which is not reached by other instruments, other multi-object multi-IFU, because Mosaic, for instance, use the ground layer of the systems and the pixel size of the pixel size. The final size is 89. And Mosaic, for this reason that use fiber, cannot reach KM, but this coverage is 1.8. So it is completely cut out of the very high resolution. The other specific peculiarities is the fact that you can align all the targets in the multi-object spectrum. This is a peculiarity that you cannot from any
This is really exciting. I've never heard of this integration. Isn't such a common idea? I thought for Amos and filled its skills. Anyway, both for this instrument and for in fact all the other spectrographs on the EMT, even the single object ones, which the function really exciting thing is that we can directly measure the mass of black holes at high regions. You have a very high telescope. So you use all the sphere inference of black hole, not only for normal galaxies, but even for quasars. You shrink the acceptor in the case of Paolo, it's 6 times the something better than it is. And it's really exciting. We can bypass, we should not be able to bypass gravity. We just go straight, to the network potential in something. We really need to study this possibility. In principle, it's possible.
Yeah.
But this is truly revolutionary. You don't need to look for AGNs. That was just that's last century, and we didn't know it's great. It's galaxies, they all have options. Just go right into the galaxy. Bypass the AGNs. Any more questions? So, rumor has it Francisco is in the house. And we didn't go to the presentation yet. So, apparently flew by helicopter. That's been on us. Yeah, that's this doesn't happen soon, I'm going to break up some of the actual team. So let's take a moment. So next is our elusive Francisco Muller-Sánchez.
Hello everyone, and thank you for the invitation to participate in this conference. As you know, I just arrived now from the airport. I was in Mexico City. So the title of my talk is dual and binary AGN from initial identification to detailed physical characterization. And this is what I was just saying a few minutes ago. So I was saying that you may go to the communities that could be related to this conference or to the things that are to us. And this is me, yesterday. And probably 2 or 3 participants from the group were with me yesterday at the airport, where we had a very difficult time with the airline. Was Polaris, unfortunately, I have to say the name. So I have to say, in Mexico City, so instead of saying, life is waiting, we must see who AGN is waiting. And they booked me for today's slide, and I was afraid today. Also, they had the same problem as yesterday, but today for those with me yesterday. So it was overbooked, it was a mess there. I had my ticket and I had to speak, so this time I had to fly. But fortunately, I'm here and I'm making in time for my talk. But yeah, unfortunately, this is the last talk of the day, and I know that you have been listening about the world and market again, and this was also the introduction, so the introduction at the end of the day anyway. Okay, so we started with galaxy mergers. We know galaxy mergers are important ingredients in galaxy evolution. According to hierarchical structure formation, galaxy mergers are responsible for the growth and formation of galaxies. We know that elliptical galaxies are the product of galaxy mergers. And in addition, galaxy mergers are important for the growth of massive black holes and the fueling of AGN. So we think that every massive galaxy in the universe has a massive black hole at the center, and sometimes those, I don't know whether it's here, okay, those black holes are active and they are called AGN, as you know. And then if 2 galaxies are merging, then in some cases we would expect to have 2 AGN, right? But unfortunately, the situation is not that simple. Dual AGN or these AGN pairs, I mean, just 2 AGN interacting are rare and they are not easy to find. And depending on the separation, sometimes they are more difficult. Of course, those separations are more difficult to find than max scale separation. And when they are very close together, we call them binary AGN. So my talk is going to be related to these objects, what we call dual and binary AGN. So this is the outline of my talk. We have 3 topics. First, definition. So I would like to talk about the definition of dual and binary AGN so that we are in the same page. And then identification. So I have seen that in the morning different talks from Sanketin, Chen, and Severini about identification of dual or binary AGN and characterization. Probably heard those by Zihuagn, Muller-Sánchez, and Saracco. And basically, the percentage of the time I'm spending these topics is probably 10% for definition, 20% for identification, and 70% for characterization. And the reason is, well, it's not only because I'm working on this field right now, and I have a lot of results that I can show you, but also I think that scientifically, this is a very important area of astronomy right now, especially dual AGN particularly. And I do an analogy with extrasolar planets, right? So there has been a lot of support discovering extrasolar planets. We know now more than 8,000 possible confirmations of candidates. So the dual AGN is having something similar. We have many candidates, we have many confirmations of many candidates. And I think that the next step, as it is extrasolar planets, characterization of these extrasolar planets. Now we have to do the characterization of dual AGN. So that's why I'm going to spend more time in this part of my talk. Okay, so let's start with definition. So we can have a very basic definition and then just say that AGN pairs in galaxy mergers are dual. But this does not include separation. So some authors are here to papers where they discuss these definitions of the Rosa 2025 and 2024. They consider the AGN, basically all AGN pairs that are and separation is not important. So you can have separation of 50 kiloparsecs, 50 kiloparsecs, maybe 100 kiloparsecs. But then the question that I have is first about the galaxy memory. Is that really a galaxy memory and the two galaxies interacting and gravitationally bound, or is it just applied by the linear separation? And also, the question is the AGN produced or the concept of the AGN is due to the merge here at 50 kiloparsec scales? Maybe the galaxies are still experiencing their own secular process or internal processes, and the merge is not really active at that moment or having some impact on the fueling of the AGN. So that's why I have this question: is separation important? And for many authors, and for the rest of the talk, actually, I will talk about galaxies that are dual AGN separation less than 10 kiloparsecs. So I was saying for many authors, this is the real dual AGN phase, and the object that we call dual AGN are those AGN pairs and separations less than 10 kiloparsecs down to 10 parsecs, which is the binary regime that I'm going to talk about in a minute. And this is supported by simulations. So here I have simulations by Pasenkoke et al. 2012, but also Lecce et al. And Capello et al. 2015 shows similar results. Basically, in the first diagram, in the first plot, we have separation in the y-axis, and this is time in the x-axis. So the separation goes from 100 kiloparsecs to 10 kiloparsecs. And we see that the dual AGN, they are orbiting each other from 100 to 15, and then maybe 50, 60, and then the 10 kiloparsec separation, which is divided by this red line, corresponds to the last 200 mega years of the merger. So here the time scale goes from 0 to approximately 1.3 giga years. So they spend most of the time on value separation by 1 or a little bit more than 1 giga year. But in the last 200, 300 mega years, the separation is less than 10 kiloparsecs. And we see that at that moment is when we have very strong star formation, so star formation rate increases as separation is less than 10 kiloparsecs. And also the volumetric luminosity of the two AGNs, so here in red is one AGN and in purple is the other AGN. Both of them increase the luminosity or they are more active at separations less than 10 kiloparsecs. So you see that this regime of separation less than 10 kiloparsecs is really the interesting regime when we're studying dual AGN. Okay, and then for binary AGN, I don't think there's so much controversy about the definition of what binary AGN is. I will just read what it says here. So it's active supermassive black holes which are gravitationally bound, forming a Clarion binary. I don't know why this shift. This is like an earthquake or something. So in this situation, the amount of gas and stars enclosed within this orbit becomes smaller than the total mass of the two supermassive black holes. And for a wide range of those properties of supermassive black hole masses, this happens at orbital separations less than approximately 10 parsecs. So we can talk about dual AGN for those AGN pairs with separation between 10 kiloparsecs and 10 parsecs, and then separation less than 10 parsecs, we call them binary AGN, so they are gravitationally bound. All right, so then we move to identification. So historically, a lot of people agree that the first confirmed dual AGN is a dual AGN galaxy, and this is 240. So these are some properties of the system with very high star formation rate of 100 per year. The separation between the two nuclei is 0.7 parsecs, so it's less than 1 parsec. And the northeastern nucleus is fainter than the southwestern nucleus, is more powerful than the northeastern nucleus. So in this image, we see the Chandra X-ray image of the two nuclei, the hard X-ray image of the two nuclei here. This is the northeast and this is the southwest. And we have also confirmation from radio, from Galileo in 2004, so it's the northeast and the southwestern nucleus. And this paper was from Stephanie Thomas in 2003. So since then, there has been a lot of work trying to confirm or first detect and then confirm these objects as dual AGN. So here I have the list of confirmed dual AGN that I found in this paper, 2017, and this is the list that I skipped because of 2025, because it turns out that there is a new publication from 2024 that is still in the archive, and I don't see the Polish version, but probably will produce soon. But these authors, they try to compile a list of all confirmed AGN and binary AGN, and a list of all dual AGN candidates and binary AGN candidates. So it turns out that in their list, there are more than 1,000 dual AGN candidates, but only 50 confirmed dual AGN. And in this table from 2017, we have 27 confirmed AGN, which means then that in the past 8 years, there have been approximately 16 to 20 confirmations, which is not a lot. I mean, if you think about that already in 2017, since 2003, there have been more than 15 years approximately working in this field, and still most of these confirmations or discoveries have been serendipitous discoveries. So not really coming from systematic searches. And the same the other 20 confirmed AGN that are in this paper from 2024. And also I like this table because in the confirmation method, as you can see here, it's always either hard X-rays or Chandra data, hard X-ray division, or radio data, DLA or DLDI data. There are other techniques, sometimes it's optical and AO, which is optical, you can take atoms or lines or lines, or the diagrams and two-line diagnosis, but those can be ambiguous. So most of these, they either have Chandra, hard X-rays, or two compact radio sources with flat spectrum being radio. So I think the situation of, this 50 confirmed AGN is because we need surveys with very high sensitivity and very high spatial resolution radio or X-ray. So I'll come to that in a minute. But most of the efforts, the systematic searches, that we have done for dual AGN, they either are in the optical, so people looking at the optical sources like SDSS, BOS, MANGA, with adaptive optics at Keck or telescopes or with Hubble, and these are some examples of papers that do this. And then they found two nuclei. Sometimes they have spectroscopy and they can say, well, this seems to be produced by an AGN based on the diagrams or the high lines, maybe broad lines. This is an example of the MANGA data where we have all this information in the IOC data for MANGA. And then you have dual AGN candidates. But you cannot say that there are confirmations on, as I mentioned, I think you get the X-rays or radio data. Unless you find a system with two compact sources in the optical that have problems. But I think that there is only one or two dual AGN that are type 1, the two AGN are type 1 AGN. So those are not common at all. So those are difficult to find. Or the other option for systematic search for dual AGN is double AGN, which are very famous technique, where we look for galaxies that in the narrowing region of all 3D mostly, they show this structure of regionalized or double peaks. This is a paper from Connor for 2012, where she has the long spectra and then the two peaks based on the P, and then because these are all green lines, they are associated with AGN. And the idea is that these two peaks are formed by the orbital motion of the two AGN orbiting around the same center of mass, and one of them will produce one P and the one will produce the other. But it turns out that this method, and these are many papers that discuss this method, it can be ambiguous as well, because many of these kinematics can be caused by either rotating these and mostly outflows. So outflows can create these spectral shades of the emission lines. So again, the success rate of this method based on confirmations of dual AGN is used to be less than 15% or around 15%. And this is something that, again, we have found from confirmations using X-ray data. And this is again, this is an example from Arcadia 266 where the X-ray is in blue and the contours of the X-rays. We have the two compact X-ray sources, and there is also X-ray emission in between the two AGN, and there is also radio contours. So these confirmations can only be done with the very high spatial resolution, which means that X-ray you have to use camera. So most of the confirmations and X-rays, I would say more than 90% of X-ray confirmations for dual AGN have been done using camera, and a few with XNN, and I think there's one or two with blue star. Again, we don't look at those variations around 10 picoparsecs, 10, 15 picoparsecs. So we need a space telescope, an X-ray telescope that give us high sensitivity combined with very good spatial resolution to do more confirmations in the X-rays. And then the radio data, so this is one of my papers from 2015, and then we have a follow-up with my student Dave Wyatt. We are studying all the public AGN from SSS within ranges less than 0.1, from at least from Commercial Data 2012. And this is what I was mentioning, that we find in all these galaxies, there are approximately 88 galaxies, that the success rate of dual AGN, as you can see here, two examples, with two compact radio sources and absolutely a flat radio spectrum for the two sources, are less than 15%. So, to my knowledge, I'm not sure again if there is a systematic search for two radio cores in galaxies with a VLA but with very high resolution. So I know this is the first survey and other surveys, but again, we don't have those surveys don't have a resolution to disentangle things like this. We have to do our own proposal and our generations to do this kind of project. So I think doing systematic searches in the radio data is complicated because they are not uniform, as I'm saying. You don't always get VLA configuration with the best spatial resolution and the best sensitivity. But it's something that maybe someone is interested in doing, right? This doesn't sound like a crazy project as well. Okay, and for binary AGN, we know that there's only one confirmed binary AGN, which is galaxy 46711. And this is the confirmation, the paper where they show the two compact radio sources, this one and this one, and this is VLBI data at 80 GHz, and they have a radio data that is associated with this radio source, and this is at 15 GHz, where we see that both of them are still very bright, so the spectrum is flat, and this is the confirmation for the two AGN in the system, where the separation here is 7 parsecs. So this is the only confirmed binary AGN today with real observation with images, and it was done by Rodriguez in 2006. Now, Lutz Fowler in 2012, she actually wanted to do a systematic search of these things. So in VLBI data, just finding two pores like this, and she found 0. So because of that effort, in 2012, then a lot of people then abandoned that idea to say, how do a systematic search with VLBI? Because it seems that the sensitivity of VLBI is not enough to detect these two objects. So this galaxy is really a special case for VLBI observations of binary AGN. Okay, but instead of using that, then we have binary candidates which are found as weird AGNs or AGN that have weird properties like this galaxy OD287, where we have periodic flares. So these are flares in the luminosity. I think this is the optical, also in the infrared, and they are periodic. So that will indicate that there is a companion to the AGN, which probably is another supermassive black hole. So this is a candidate. Another one is this interesting object, which has sinusoidal light course. So for an AGN, you expect the luminosity of the source to be constant or has some variability, or periodic in, I don't know, larger time scale. But this is a sinusoidal function, and we see for a sinusoidal planets from all stars. So again, this is a strong indication of problem is a binary. All these galaxies from 151 where we see the same, a similar thing here, the sinusoidal function, but for the velocity. So these are velocity oscillations which could indicate that a galaxy or an AGN that is moving to the pericenter and the apocenter and then changing with time. And the other methods are multiple jets or outflows. So we have radio wavelengths, and one that is very promising, and I have explained this, is a helical radio jets. So these again are systematic searches of objects with helical radio jets that indicate that the precession due to the binary is causing the jets to change orientation time, and they form helical radio jets. And finally, there are spectroscopic methods where we look for double peak or offset emission lines in the broad region. So for dual AGN, this is done in the narrow region. For binary AGN, this is done in the broad region. But, as it was the case for dual AGN, the same situation happens for binary AGN, where these double peaks can be caused by kinematic, right? Creating these or by outflow. So we have to be very careful with these candidates. All right, so that was the identification, confirmation of this dual and binary AGN. And the last part is the characterization of these objects. So I started a project that is called Multi-Wavelength Observation of Dual AGN, or MODA for short. And what we try to do is to combine data with wavelengths to characterize the environment around confirmed dual AGN. So we'll show a couple of examples for three galaxies, mostly NGC 240, Mercalli 266, and ESO 509. And here we have a result from NGC 240. This is my 2018 paper, where we discovered dual outflows in NGC 240. Basically, here we show the results. So we have a star-driven outflows to the east, or to the west. So it would be the northwest and AGN outflow to the northeast. So basically what we mean is that combining data from radio, near-infrared, optical, Hubble data, and X-rays, and of course, near-infrared spectroscopy and optical spectroscopy, we were able to dissect the butterfly. So this is called the butterfly nebula in this 240. This is the shape of the butterfly here, and we analyze each region individually. So again, another movie that could be related to this result is the butterfly effect. I like a lot. And then this is basically what we did. So we have an O3 image of Hubble. It's a Hubble image of O3 emission in blue. And you can see that it's mostly extended in this direction. And almost shows like a conical shape as well here. And then we compare that with the molecular gas. This is near 2, so it's a filter at H2. And then we see that there is no molecular gas emission on the position of the O3 emission, so that can be inflows or gas that is in the disk of the nuclear galaxy. Then we have emission line diagnostic diagrams where the cone, the O3 cone has mostly this part with cipher line radius, or some of them are line radius. And finally, we have the kinematics from Symphony and data from the AP observatory as well. So here very quickly we have the flux of the stars, the molecular gas, and the ionized gas and bracket gamma. And then we have the velocity mass of the star, and you can see that we have two rotating disks here for the north nucleus and the southern nucleus. The molecular gas has complicated kinematics that actually indicates string motions between the two nuclei. And finally, the ionized gas shows a very different kinematic structure from the rotation of the stars, with mostly restricted gas here, which is the base of the bubble, the H-alpha bubble. And here I show that actually this corresponds to the base of the H-alpha bubble, so this is how we conclude that this is a star-driven outflow, and the O3 cone on the other side is an AGN outflow. And then we have some results here, some numbers of mass flow rates, time scales, and energetics. And the important result here, well, I think all the numbers are important, but particularly I would like to compare the outflow rates. So for the O3 cone, which is a medium outflow, which is 75 solar mass per year, which is huge. And for the H-alpha bubble, it's approximately 10 solar mass mass here. Now, I mentioned that we have other galaxies. So here I show results for, well, we have already seen this is 240, this is Mercalli 266, and this is DSO 519. And it turns out that for these two galaxies, for Mercalli 266, we will take only compact outflows of silicon seeds. They are not as extended as in AGNs 240, and outflow rates are similar to what we see in different galaxies around 1 solar mass per year. And in this Zihuagn, the situation is that we have an asymmetric outflow. So this galaxy on the left and on the east does not have outflows at all. Actually, the spectrum of this galaxy looks like an galaxy in the infrared up here. And all the activities happening now in these nucleus, in the western nucleus. So it's like we have one active nucleus and the one is not active. So it's a very different situation. And here the outflow rates are also around 1 to 10 solar mass per year, so they are not extreme. So I think that one of the interesting conclusions is that these are different separations, right? So in fact, NGC 240 is, like I said, only 7 parsecs. Mercalli 266 is around 6 kiloparsecs separation. And this is one of the largest separations that we have in our galaxies. DSO 519 has 11 kiloparsecs separation. So we are adding 5 kiloparsecs from here to here, and then another 5 from here to here. So I think separation plays a very important role, and this is what I was saying at the beginning of my talk, that this is an advancement that is 240, and here a lot of things are happening in the central region that is causing inflows and outflows. Whereas here the separation is 6 kiloparsecs, so the Mercury is producing some activity in the two nuclei, but it's not as extreme as this. And these that are at 11 kiloparsecs, we have one nucleus that is on and the other one that is off, right? So we think that we need to study more that. So like I said, it's a new field that I know that a lot of groups were starting to do this characterization with AGN, and I think it's a very exciting field to see what we find. And then in this slide, I also show the inflow. So this is a diversity in dual AGN feeding, where here what I'm showing are the velocity maps of molecular. So for NGC 240, this is something that we have seen in the previous slide. We have gas streamers that are moving from one nucleus to another one. And we see rotating these for one galaxy and for one nucleus and for the other nucleus. And we call these cross-streaming, where the two AGN are fooling each other. In Mercalli 266, we do not have evidence of gas streamers from one nucleus or to the other nucleus or pilot phase or anything. We see only these processes. And again, by fitting, rotating these models, we find that these structures that we find here are similar to these system galaxies, like pilot arms or bars. And finally, for DSO 519 is the situation that I was telling that we do not have any H2, we didn't detect any H2 in our integral data for these nucleus, and everything is happening in the western nucleus, and we detect this structure of molecular gas that has this velocity, and it appears to be connected and coming from the other nucleus. So we actually conclude that this is evidence for an asymmetric fueling where these galaxies currently in fuel and the other ones is starting, or at the moment is not active in fueling mechanisms. I'm sorry, I don't know what I was going to do. So here I showed more results about these. So if you're interested, we can explain there's more maps about the same galaxies, about the outflows and the inflows. And then the last thing I want to mention is the characterization of the only binary AGN that we know. So 4, 6, 27, 11. Of course, we cannot resolve the whole nuclei here with any other telescope that is not the BMI. But at larger scales, you can see the scale is 5 arcseconds, 6 kiloparsecs, the bar here and here, the same scales. We have X-ray emission here in black and white, and the red contours correspond to radio VLA data. I think it's at 8 gigahertz here, and the blue contours are the same here, but this is VLA at 15 gigahertz. And what we see at X-ray is that we have extended X-ray emission, like an X-ray halo. By the way, the host galaxy of the binary is an elliptical galaxy, so 40% length is an elliptical galaxy. So we have this X-ray emission, we have an extended range where these all courses from Romanian Plan 2014. they identify all regions of the radio jets of A, B, C, and D. In the 15 gigahertz, we only see A and B, but we see this chemical structure of the radio or an S-shape, basically the jet seems to change orientation as it propagates in the interstellar region of the galaxy. And therefore, I would say that this seems to be a smoking gun for binary AGN because we see it in the only binary AGN we have confirmed today. In addition, this image shows B minus R map, or rather B minus B. So it's a color map where we can see in white some structures that resemble like spiral arms or gas flows into the nuclear region. So that would be very important if we could understand the central region of this galaxy to see if there is enough gas or stars or evidence for inflows into the very central region where we could argue that the binary could be replenished with new material and eventually solve the last passing problem, which is a very important field, a very important topic in exact astronomy. So I think the characterization of this galaxy is crucial, and it should be done with very high spectral resolution and with several negative spectrographs. And with that, I will finish my presentation. I just want to say that we have a candidate for a sub-parsec Gaussian black hole binary in C488, which we discovered using the same method as the confirmed binary AGN for 711. Which is a chemical structure of the radio jets, but not only the radio jets, but also this is a molecular gas that is rotating basically from east to west. But in the silicon 6, so this is the money in this slide for this galaxy, we see a rotating cone. So the outflow is perpendicular to the rest of the galaxy, so it's moving away, and at the same time rotating, which indicates helical movement. So we fitted a model with a helical outflow. This is our results. This is a whole image of the galaxy, and we see that if we let our model run at larger scale, we can reproduce well the morphology of the whole emission in this galaxy. And in addition, as I was saying, here's where we basically eliminate options that are other than the possibility of the binary. This is our interpretation, so two supermassive black holes vary from each other, and they are misaligned with the plane of the accretion disk, and that will cause the precession of the outflows and the precession of the radius. And as I was saying, the radius is also bent, showing like a S shape here, as well as the masers, they are also bent. So we have another binary candidate in NC488, where the new idea that they are proposing is using heat outflows of ionized gas. All right, so these are the concluding remarks. First, we can talk about some concluding remarks and some future prospects. So first, I think we need more sensitive radio and X-ray surveys with high spatial resolution to detect them and involve dual AGN and if possible binary AGN, although that seems to be more in the future. In the near future, observations of binary AGN to their low frequency gravitational wave emission promise to be revolutionary in our understanding of the formation and growth of massive black holes. It's something that I've been covering in this talk, which is gravitational wave emission from binary AGN. So that's out of the scope of my presentation. It's a very important topic in the future. And like I was saying, we need to characterize the only confirmed binary AGN to better understand the mechanism of supermassive black holes and the last part of the problem. I have more here, so these are some questions that we would like to answer with the model survey. So how are supermassive black holes doing in galaxy molecules and what are the infrareds? The same thing for outflows, that's number 2. Number 3, a dual AGN consistent with the standard information model of AGN, so they show all the components that we know from the accretion disk, radius, the torus, which we are not sure, especially the torus in these objects. And finally, what is the role of galaxy analysis and fusion AGN in galaxy evolution? So these are my last slides. I'll go very quickly. These are topics that I mentioned this talk, I didn't emphasize or I didn't cover here. So AGN pairs a separation with the larger and technical parts like I said. I don't know if this is the dual AGN regime, we can call it, but it's important to study these objects as well. multiple AGN systems, so not just duals or binary, but for example, it's a triple supermassive black hole or a triple AGN, where we have information from this guy, and this guy. And then we have offset AGN, which means in a merger, one black hole is active, but the other one is not. So some people call this offset AGN. And finally, gravitational wave recording supermassive black holes, where we have a binary that is about to merge, and then in this process, we see gravitational wave emission, and when they are very close and the gravitational wave is very strong, the two black holes merge and then speak out from the center of the galaxy, and we see in a second. Okay, now, and it's escapes from the nucleus. So this is a gravitational wave recording black hole, and we have some candidates for this, which is this galaxy Cosmos J1000, where the black hole, I mean, we know it's an AGN because there is hard X-ray emission coming from the galaxy, or the nucleus in the southeast source, but it's not at the center of the galaxy. So this is a very strong candidate for a gravitational wave recording black hole, and actually we have a interesting proposal for this object in the future, and see if we can confirm the nature as a recording black hole or not. So yeah, thank you for your attention, and this is my really message to my students, and I'm open for questions.
Just a comment that I wouldn't say that there are only few type 1 engineering. The work was using astrology or big or GP show that we found like tensor conversion higher redshift and multiplication without the it's very good instrument to find this system. Okay, your bias towards mixed objects, but
yes.
And it's like something like no, okay, some of them are not published yet, but we have something like 13 systems last 3 years.
Okay, yeah. So, I agree, and yeah, I would like to see it. Go forward.
I think it's for the next one. I just want to point out that I did a paper together with Luis Bernard. This was covered. We discovered that there is a viable source in NHC43 again.
NHC43?
Yeah, the one that yeah. So they look at the paper maybe to help because it's a type 2 engine, right?
It's
type 2 and it varies. So we discovered in observing different times that it varies. So maybe it's some indication powers right.
Yeah, sure. Thank you.
I was going to ask you about H2. You rely a lot on H2 emission.
Yes.
Can you explain a little bit more about why you expect H2 in both the AGNs?
Okay, so there are technical reasons and scientific reasons. So the technical reasons are, you can find these transitions of one molecular hydrogen in the near infrared. So many of the isotopes there. So that's why we use H2 in the near infrared. But also take velocity, right? So the take velocity at those grades between 1 to 5 microns, we have a lot of transitions, so I think it's important to understand them very well. And scientifically, we know that this is more molecular gas. So I have some certain people who talk about we really tracing the same gas as the all molecular gas in ALMA, for example. And my answer is that at least for the objects, which is, also a lot, I would say between 5 to 10, so around those numbers, the kinematics and the photons are very similar between all molecular gas and one molecular gas. So it's not a big sample, a large sample, but still I think it's useful to use molecular patterns as a tracer of the molecular gas, and then see, like I said, some examples where we can compare with ALMA, see if there is a good correlation between photons and kinematics, and then we can say what is the whole molecular gas moving from this is an outflow, that would mean that there is a pressure in star formation with all gas in star, or things like that. So yeah, we are using that as a tracer of the molecular gas. And we also have found that is also work for all that like ELSA here or other groups. It's a good tracer for inflows. So we are also using it for inflows.
I was wondering, a bit related to one of your questions, the whole this whole question. So how important actually is dual AGN for the growth of the black holes? And how does that relate also to how is your findings and everything related to particular simulations of these last 200 million years where there is this intensification rate on the other hand?
Yeah, so I think this is related to what I was saying that separation seems to play a very important role. Unfortunately, I mean, an example, so I would like to do, or my colleagues trying to do all the updates in the table that I showed from Saracco 2017, which is 27 confirmed AGN. So we would like to do basically there spectroscopy in the optical and the infrared. But it's very difficult to get all the data. So we have observed probably like clouds for those objects, the ones that are more famous and very nearby. And this will have more statistics. But my answer from now would be that separation plays a very important role in this question, the feeling of AGN due to galaxy networks.
But you say that this dual AGN is an important part of the black hole growth, or is it just like 1 or 2% of the black hole that is in this phase? Yeah, is it more secular accretion that is the dominant black hole growth method?
Yeah, so for the galaxy we have studied, I think the important number to say is the inflow rate. So for any CP240 where we have very large inflow rates, also considered with very bright AGN and large black hole masses. But for the other two, for my 1066, the black holes are there 1066 and 7, and the inflow rates are also not as strong. So I think depending on the separation of the object, we'll see different processes. So this is why comes from the sort we have done until now, where some galaxies are still showing internal processes of these processes to the progenitor galaxies, so there is no real impact on the merger. And in others, when the separation is getting smaller and smaller, then the gas inflows from mergers are very important.
Yeah, coming back to the type 1 or 2 problem, you mentioned that the characterization is very important, because 70% of the time we talk about the characterization. I was wondering if you could use channel data, X-ray data to characterize the level of obscuration of the 2 AGN. Can you comment on that?
Yes, we have done that for NTC240 and SO509, and that's one of my conclusions for SO509. We see a very strong obscuration in the eastern nucleus, the one that I said is showing activity, but it's highly obscure, that one. So, yeah.
So the 2 nuclei don't show the same level of obscuration?
No.
And so why is it not done for the other rest of the dual candidates? Because you said you have channel data and information for most of the order.
So the cancer study, yes, we have channel data for this.
So let's say the 20 or so.
The 27?
Is there a systematic study?
Yeah, so for those 27, I think there is, and I'm not 100% sure about 27, but I'm sure, I mean, we can go to the table very quickly. And we can see many of them say they have channel, and it doesn't say, yeah. So this is the RBI, optical and radio, this is Chandra, optical and radio, Chandra. Yeah, so for many of them, yes, we can use Chandra, but I'm not sure if all of them have Chandra. I think it's one of the questions where my collaborators who are experts in X-rays, they are trying to get, well, I don't know. I think Chandra is still work in as opposed to communicating through. We had the last cycle, but there was no funding. But yes. Yeah. Yeah.
I'm sorry. Two last questions. So, for 40 inches, we're creating outflows for the OPS. Can you explain a little more how that would work? And yeah, just
Okay, so let me go back there. So first, I know I remember quickly those slides. We start with, okay, so first thing, now I have an visualization, the real orientation in the sky is actually 90 degrees. So it goes, this goes from east to west to east down here. So this is the data that we have from Osiris. This is the O3 image, the whole O3 image that I showed later as results. And then here I have the Viva survey, which is large scale atomic gas or neutral gas. So it shows the rotation of the galaxy because this is R minus and this is R seconds. So this is the rotation, this is molecular gas by the way, so the rotation of H2. And we see that it's basically the same orientation as the large scale is at smaller scales. Although there is a small change of position angle where it used to be like 78, 80, and here is a little bit larger than 90. But yeah, it's basically very similar. And then the interesting result is being with silicon seas, where we have seen in the previous slide that the rotation occurs in the disk of the galaxy from left to right or east to west. And here, at the location of the outflow, we also know that there is the O3 cone and the O3 outflow. We see this structure of velocity of silicon 6, where the gas is not only moving outwards, but it's also rotating. So we see residual velocities and residual velocities that are coming out in the south. So this is what we interpret as a rotating cone, which, if you do the geography, that's it's a helical outflow. And we also see very high dispersion in this region of silicon 6, which is also a typical indicator of an outflow, in this case of silicon 6. And then,
so just go back and then, physical, how are you physically getting your clouds to be rotating in general effect? So maybe you're saying that the radio is traveling on the magnetic field line. How are you going to get your clouds to be traveling in that direction?
So this is a processing outflow. I mean, I don't know that's what we're referring, but everything starts with the accretion disk that is processing, and that's how we get the grains that are also processing, following the rate that I showed in a slide here. Although it's this one here in purple.
That's the radio, right?
This is radio, yes. I think the green, I don't remember what the green is here. But the radio jet is in purple here. And this is assumed of their, because collaborators pass me this radio image. So what you see here in colors is the same as this purple region here.
Right, as the whole gas, are you saying that if you set that one slide, are you saying it's following this schematic model if you set that one slide?
So where?
One more, sorry, that. No, the cursor. So are you saying that O3 gas is following one slide back? Yes. Are you saying that that's what O3
Yes. So we are saying that the origin of the AGN rim is perpendicular to the accretion disk, so it follows the radial as well. Yes.
All right, final. I was a little confused. Do you really know why AGN is because they're all
yeah, that's a very good question. And this is this slide is where I have my answer. So you can have a single black hole that is misaligned with the accretion disk and you can get recession. So these are calculations for radiatively induced warping, the lens spinning effect, which is a relativistic effect, and anisotropic accretion events. And we found that the numbers are not consistent with the scales that we see the origin of the precession or the time scale of the precession.
What are the separation of the
let's see if I have a period here, the period 1.6 megayears, and the separation, well, I can tell you from this slide, because here, these are the masers, so these galaxy has a maser disk. And these are the masers that are rotating the blue, so red sheeted is blue sheeted. And our binary is basically inside the maser disk. so it's less than 0.28 parsecs radius. So yeah, it's smaller than what is predicted by those specs that I showed in the previous slide. Yeah.
All right, let's thank Francisco once again.
Okay, City Council confirmed the total release this afternoon, so if you want to watch that, it's going to be at 6 p.m. Let's meet on the restaurant of the dinner, which is La Perla in Playa La Ropa. It's going to be very close from there. And if not, if you prefer to go directly to the dinner, let's meet 6:30. But we suggest you to come to the total release. Also, the sunset there is beautiful. It's going to be like 6:15 or 6:20. So everything is going to happen between 6 and 6:30. So let's meet there. Have a good afternoon. Have a good free afternoon.
Esto hay que quitarlo, sí. No sé si nada más se quitan los cables, sí, ¿verdad?
Hay que apagarlo, ¿no?